Okay, and okay, so I hope the screen is visible.
Yes, ma'am.
Yes. Okay. So where we stopped last time, like before the exams, was in Q-learning, right? So just a quick recap was it was a version of MBPs that we were looking at, where you had some states and you had some transitions, some actions to take you to different states. Okay. And so the thing was, you had all these components, and the issue was you didn't know the transition probabilities. There was a probability of reaching another state, S dash, from a current state in action, but you didn't know these probabilities and you didn't know these rewards. Okay. And you remember the discount factor. So the immediate reward you get when you take an action A from a state S, and if you land up at S dash as R S A S dash, and at the next point of time, what you're going to get is discounted by gamma. There's a gamma factor which comes in, and it goes on and on. So, what you want to do is ultimately you want to find a policy which is a mapping from each state to the set of actions that you can take. And you want to find the policy that maximizes your long term rewards. Okay. So the long term rewards was something like you had, the reward at time one plus gamma times the reward at time two plus gamma square times R3 and so on. And this is something that you wanted to maximize, and that was decided by the action that you take. Okay. And in RL specifically, you didn't know the probabilities, and perhaps you also didn't know the reward functions. And it was just like an open system. I mean, a system where you don't see anything, but you have to somehow estimate these parameters, or somehow estimate what is the best action for each state. Okay. And that's where what we were doing. And we saw model based, model free learning. And there were a couple of questions here. So one was the value of a fixed policy. How do you estimate that with data? So that we started off, and we developed a method for it, and that was called temporal difference learning. Okay, so where whenever you observe the transition, you just make an update to the value of the states. Okay. So that was temporal difference learning. And the reason why it was called this temporal difference was there's a difference here which comes up from the new sample and your old estimate. Okay, so that's why it was called temporal difference. And this was the sort of algorithm for each state. You see the action is fixed, it's always prescribed by the policy, and you observe the reward, and then you make an update to the values. This is what you did in temporal difference learning. Now, what we said was that this was a passive approach where you follow the actions explicitly given to you. You don't have a choice of deciding what action to take. So in that sense, you cannot learn the optimal policy using temporal. So, to recollect, this Q state was kind of an intermediate step where you take an action from a state. So, from S, if you took an action A1, there was an intermediate state that we represented called the Q state. And after that, the environment plays in and you get some other S dash. Okay. And so, what you try to learn is the optimal value corresponding to the Q states rather than the V states. Okay, so the essential idea was to use these Bellman equations, but rather use it for the Q states. And this was the update that we saw. So suppose you see S A S dash R. So this is the transition that you have seen. Then, and if you maintain a running estimate of the Q values. So this is going to be a function of the states as well as the actions. It's going to be like a table. And finally, what you do is when you see this transition, you make this kind of an update. Okay. Your new sample is basically, I mean, it comes from the idea that you're trying to approximate an expectation. So what you do is you take a sample of this quantity, this R plus gamma V star. So that's your current reward R plus gamma times the max of Q at the new state S dash, okay, and the max over all actions possible from S dash. So that is your new sample, and you use that to update your Q estimates. Okay, so this was the Q learning algorithm, and then we also saw how you do exploration with Q learning. You combine exploration with Q learning, so where you decide what kind of transitions you want to see. Okay, so at every point you want to do well, but you also want to explore some parts of your state of your states and action space. And so what you can do is, we saw this epsilon greedy kind of um, method. So where you take a random action with probability epsilon, and with 1 minus epsilon, you take the best that you've seen so far at each state S. Okay, and then you observe a transition, you keep on doing this. Okay, you update your Q values, and then again you try to make another transition, and you keep doing this. Okay, so this is where we stopped before the exams. And what I told you was, with epsilon greedy, there are some guarantees that it converges to the optimal policy. Okay, and what I wanted to tell you next is, yeah, Q-learning works well. Okay, it's a reasonable approach. It has guarantees and everything. But what do you do when you have like a huge number of states? The issue is that, you update a Q state, a QSA. You update it only whenever you see this tuple SA, right? Whenever you see that, you update QSA. Okay, now if there are a lot of states, then you will have to ensure that there are enough samples, enough transitions have been made to cover all these states. Okay, so let me just show you an illustration of this fact in maybe Pac-Man, what these different states, how it can be. Okay, so I'll just show you this one. So suppose this is one state, okay, in a Pac-Man game. Okay, so the state is characterized by the positions of the food, position of Pac-Man, position of the ghost, and there's so many parameters. Okay, and in our first class we saw that there can be a huge number of states. Okay, now what I'm going to show you is one more state here. Okay, so what's the difference between these two states? Is there a huge difference between these two states?
No.
No, right? I mean, it's actually a symmetric version of, like state two is a symmetric version of state one, where, Pac-Man is again on top, and, you have it's surrounded by ghosts and there's some food. Okay. Now, what Q-learning will do is, state one and state two are two very different objects, two very different entities. So if you have to, figure out the Q values for state two, you should have explicitly seen state two in your transitions. Otherwise, you cannot learn anything about it. Okay. Though, if we, how do people learn, right? Like if you see something like this, you know what is going to happen. You can gauge what's going to happen in state two also, right? But Q-learning doesn't really allow for that. Okay. Now let's take one more example. There's a state three here. Okay. So what's the difference between state three and state one? Is there any difference?
One particle is missing.
One particle missing here. Okay. So whoever caught it, like, was it Advait?
Yes, ma'am.
Okay, it's a very keen eye, very sharp eye. So it took me a while to figure out really what was the difference between these two. So it's just this one particle here at where my cursor is pointing, that's just not there in state one. I mean, sorry, in state three. So state one has a particle there, whereas state three doesn't have one particle. That's the only difference. But just for that, you have to, somehow ensure that you visit state three. You do some transitions with state three. So it makes things very difficult when you have like slightly larger state spaces. And in fact, even for not too large spaces, like if you even just slightly increase the state space, also the kind of effort is a lot. Okay, so I will show you a demo in some time for that. So the idea now is, can you exploit what you learned about state one to, make a judgment about state three or state two? Okay, so can you generalize something that you learned from state one to these other states? Okay, so that's going to be the focus of today and maybe tomorrow also. So this is the notion of approximate Q learning. So let me just start a new page. Okay. Okay. So yeah. So what we'll do now is this concept of approximate Q learning. Okay. So yeah. So again, the Q-learning update was for, if you saw a state A, S dash, and R. If this is the thing that you saw, the transition, what you would do for Q-learning was, I'm just writing it in a slightly different way. So you would take your current estimate plus alpha times R plus gamma. So S, you see an action A, you go to the Q state and then finally S dash manifest. So gamma times max of what happens in S dash, right? So max of A dash Q of S dash A dash. Okay. So this is what simple Q learning was going to make you do. Okay. So was this right? Or this has difference term also, right? So minus QSA also. Okay. So alpha times R plus gamma times this max term minus QSA. So this is the original estimate, and this is your new sample. Okay. So this is what you did in Q learning. So now the idea is, instead of making this depend explicitly on what you've seen before, can you have some structure to this Q function, because you're trying to generalize things. So this is kind of like what you saw in min-max games. Like you saw this notion of evaluation functions, right? So can we do something similar here? So the idea is, if you have some features, so maybe let's just call it f1 of SA, f2 of SA, like that, up to fn of SA. So you have some n features. So maybe it's again like the closest dot, position of the closest dot, um, maybe the position of the closest ghost. So maybe the closest ghost or anything. Okay, so you can define things the way you like. And so these are all the features you think would matter. Now, what you can do is you can just write the Q function. So QSA, this is, we'll call it a Q function. So you can just write this as a sum of some weighted, weighted sum of all these features. So WIFI is A. Okay, the sum of all this. Okay, so it's just W1 F1 SA plus so on plus WN FN SA. Okay, so these f values are something that you would be knowing beforehand. I mean, it's something which depends on a state and an action, and there are some weights that you give for each of them. And remember, in min-max kind of games, what you did was you were trying to tweak these w's to see something that works, right? You were doing the task of actually tuning it. But now what we'll do in difference here in Q learning is that you are actually going to learn these w values. Okay, so learn the w values from the samples, learn the W estimates from samples. Okay, so again, the idea is going to be that the data you see will be like of this form itself. You're going to see SA, S dash R. This is going to remain the same. But what you're going to do is you're not going to maintain a QSA, but instead what you're going to maintain is these W's. Okay, so you're going to keep a set of weights W1 up to Wn. Okay, and each time you see a sample, you're going to somehow update these weights. Okay, so now no more q values are going, these q explicit values are not going to be stored. Okay, so the idea is, since you have this kind of a representation for the q values, now any other state you see, so suppose you see a q s double dash, okay, and some other action a dash. So what you can do is, you'll be able to compute these features. So you can compute f1 of s prime a dash, let's just call it a double dash to be just consistent. Then you can compute f2 of s double prime, a double prime, and so on up to fn s double prime, a double prime. And what you can do is, now with the weights that you learn, you can just combine all of them. Okay, and that immediately gives you an estimate for the q value for a different state action pair. Okay, so all you need to care is about these weights. How do you update them based on your samples? Okay, and to do that, the update will look quite similar to what you did in vanilla Q-learning. Okay, so let me call this vanilla Q-learning. Okay. Vanilla Q-learning had this kind of an update. Now, what you're going to do in approximate Q-learning, so in approximate Q-learning, you will update the W's. So you will update each WI like this. So you'll have your current estimate plus alpha times some difference term. Okay, so I will tell you what this difference term is. So this difference term is exactly like what you had here, a sample minus the original value times, there's a difference here. Here you're also going to weigh it by how much each feature value is. So what you see here is, you observe S A S dash R. Okay, this is a transition that you will observe. And now you will update the weights. These weights are common. And you will weigh each update with a value of Fi. Okay, and corresponding to whatever transition you saw. Okay, so let me just, yeah, this is one term. Okay, alpha times this difference times Fi. Now, so that's the difference from Q-learning. This quantity here, that is different. That was not there in Q-learning. Okay, and I will tell you why this works. And this difference term is actually supposed to mimic exactly this, whatever you saw with Q-learning, the same term. Okay, so let me just write it here. So this was R plus gamma times max of Q S dash A dash, okay, minus QSA, right? This is what we did in Q learning, in vanilla Q learning. But now we are not going to maintain these Q values, right? So how will you compute this? Is the question clear, like what I'm asking?
We can generate the Q values as needed using summation WF.
Exactly, right? So, so you are not going to store these Q values, but what you can do is use this formula to compute this as well as this, right? So, and then you just plug it into these different. So this computation of this value is not difficult, right? So here what you will do is, you will use the old estimates. So let me call this Wi new, and this is Wi old. So to compute this, what you will use is the old estimates. So this you will compute it using W1 old, W2 old, and so on. Okay. And yeah, right. So it's simple, right? I mean, it's a simple update. Okay. And we will see why it works. I'll give you a reasoning for why this works. It's actually a generalization of linear regression that's being used here. Okay, so I will explain that to you, but I just want to pause here and ask, are there any questions on this? Was this clear, the approximate Q-learning, the algorithm?
Yes, ma'am. But I have a
Yes.
question.
Yes, Andre.
So in this algorithm, we also have to somehow choose the best functions f. So won't that make it a bit more difficult? Because if we don't choose the correct f, then we won't get the correct uh, path.
Yeah. So these features, these values, right? That's what you're saying,
Yes.
right? Yeah. So it's very sensitive to what kind of features you choose. Okay. So that is a design choice that you make. Okay, as a learner, and you also, it also helps to have some idea of the domain. I mean, what kind of problem that you're solving. So here is where, like, if you have a better idea of the problem that you're solving, you can design better features. Okay, so this is, yeah, there is a lot of possibilities here into, it's called actually feature engineering, so into designing better and better features. And so yeah, so there is no like clear answer for what set of features works best. This is something that you just try things out experimentally, and then you observe how your model is performing, how your learning is improving. Okay, and then you try to think of other possibilities, what other features might be helpful, and things like that. Okay, so yes, so that is a design choice that as an AI practitioner you make. Okay, it's a design choice. And another thing I also want to tell you is this particular function, right? This linear combination of these features, so this is actually called a linear Q function. Okay, uh, right? So this is a simpler form. It's a linear Q function because it's a linear combination of these features. But you can use even complicated values here, different kinds of functions. You can use a polynomial here, for instance. You can you can use practically anything here. Okay, but only thing you have to ensure is that you're able to learn properly. So in the case of this model, there are just these n parameters that you have to estimate. Okay, and so it depends also on the amount of data that you have. So nowadays, there is this thing, people have started using deep learning kind of functions here. Okay, some kind of a neural network in this Q function. So in fact, even I think I sent you this one. There's a workshop that's happening on deep reinforcement learning. It's starting tomorrow. Okay, so next 3 days there's a workshop being organized by ISC. So that the theme is deep reinforcement learning. So what they do is, I mean, just at a very high level, in this Q function, you represent it with different kind of models, and one way is to use deep learning here. Okay, so generally, this actually whatever I've shown here, this linear Q function, it comes from linear regression. So that's a model in machine learning. I mean, many of you might have read about it, but generally you can use any other learning models also. Okay, but just you have to ensure that it's not an overkill. Okay, so that also depends on the application. Okay, so yeah, Advait, is your question answered?
Yes, ma'am.
Okay. So, are there any other questions? I mean, the rest of you are all very quiet. I want to know what's going on.
I think we need to probably like watch it again to understand it more clearly. Like I've got an idea, but not clear too clearly.
Okay, so can you tell me which part is, I mean, which is the part that you're having some confusion?
That functions evaluation part.
This one?
Yeah,
Okay, so you understand what these features are? Let's go maybe step by step. These F1, F2 up to Fn. You
yeah,
understand what those
the
are?
functions. Yes, yes.
Th- Okay, so those are some kind of features to represent each state and action pair. Like what I mean, those are like some additional things that you have about the state. Okay, like an example I gave was with Pac-Man, things like this. Okay, and instead of exactly capturing the Q value directly, you're trying to extrapolate it as using these features. Okay, and these features for a given state and action pair, you'll be able to this, you know how to compute. Okay, like things like this, right? The position of the closest dot, this actually doesn't even depend on the action, right? Or you can also define it as a position of the closest dot once action A is taken.
Ma'am, my one of my doubts is that like earlier when you showed three states and as like the first two are kind of same, don't we consider these features like position of the closest dot and all in the as a part of state space, or like do we consider them separate from for each state?
Yeah. So in the way, I mean, so there are different ways you can represent your state, but typically the state is represented as, a set of locations where you have food, right? Or a set of locations where there are the ghost or this or the location of Pac-Man. So it's a tuple containing all these things, right? And you okay. So there are these coordinates which are there, a set of coordinates. But you may not have like explicitly this. I mean, of course, you can compute these features using the state representation. That is possible, but it's not explicitly stored there where the closest ghost is, or how far you have traveled so far. Okay, things like that, or how far you are from a pellet. It is computable using the states for sure, but it may not explicitly be part of the state information, right? And right, Tanuja, is it clear?
Yes, ma'am. So basically, we can extract the features from the given state.
Yes, exactly.
Okay, ma'am.
Okay. So here it could be that you in state one, if Pac-Man decides to go north, there's a new state that is reached, right? If he actually reaches there, and if the ghosts are here, so then you can have a feature which says at that point what is going to be the difference, like how far is the ghost going to be, and things like that. Okay, so it's completely open, it's a design choice you make, and that's how you will compute these f, but you'll have a clear well defined way. Once you fix the features, you will know how to compute it. Okay, it's not that even you don't know how to compute the features. That's not the case. You will say that this is a parameter that you're going to use, and you will know how to compute these also on your own. Like given a state and action, you will know how to compute these. Okay, so exactly like how you saw in evaluation functions, the same idea here, and then you will combine them with these weights. Okay, and the weights is what you will learn. The features you will know, this f1 to fn you will know, and the weights you will estimate from the data.
And
Okay.
when you said we can have polynomials as well, uh, like in the polynomial, is the variable the function or the weight?
It's always the weights. The features are always known. So what you could have is maybe something like this: w1 cube times f1, something like this, right? Or w2 square, something like that, right? You can also have polynomials like this, right? It's a more complicated function. I mean, this q function is overall it becomes more complicated, right? W2 square
Okay, ma'am.
times. Okay, is that clear, Tanuja?
Yes, ma'am.
Okay. Uh, sure. So, any other questions? Does anybody have more questions?
Ma'am,
Akshay
there is some
Jeswal?
questions in the
Ma'am,
chat
chat
box.
box.
Oh, okay. So, why those evaluation functions should not be an overkill? Yes, Karthik, those evaluation functions can be an overkill. So, so there also you have to, design it carefully. So, nowadays people are using deep learning, as I said. So it's not the case that for every application it will work well, but sometimes if you have like a lot of data, then people are observing that some of these choices are actually working out. So that is something that you have to keep in mind. You shouldn't design something which is like too complicated that when learning becomes hard, and that is something that you should keep in mind. So this kind of functions, is linear functions, are easy, right? I mean, it's not it's less likely to be an overkill because they're just going to be n parameters. So if there are 10 features, they're just going to be 10 parameters here, but your data typically you'll have probably in thousands. Okay, so then it's not too bad, right? At least in machine learning we have this, I mean, you'll probably see it in the next semester, but there are these kind of rules and these broad guidelines which say that, if your data is about 10 times more than the number of parameters, number of instances that you have is 10 times the number of parameters, then you are kind of safe. Okay, so it's a rough guideline, but yeah, depends. It's very much dependent on the domain and things. So yeah, this is something that you have to keep in mind when you design your Q functions. Okay. Um, okay, so I
Ma'am,
think
so in all, we just have to keep this evaluation function simpler, as simple as they can get.
yeah, as simple as they can get, but also, adding some more, if you add some more complexity, it makes it more expressive. So it's like a trade-off, right, between how much you can express and how much you can learn, right? Right, so a
Got it.
complicated function, right, I mean, you can capture very general things, but you should be able to support it with the data, right? So that's the trade-off you need to make. Okay. um, Good. So, okay. So, I think we don't have time to proceed further. So, what I'll do tomorrow is I will tell you why this kind of an update is going to work. Okay, it actually follows from linear regression. It's exactly linear regression that we are doing here. Okay, but I'll just show you what it is, and so maybe that will introduce you to linear regression if you have not already seen it. Okay, and then I'll probably show you some demos of how this helps in Pacman. Okay, so I've been giving you examples with Pacman, Grid World, and also that you can actually visualize it in your labs. But this is generally like very open, even like it has a lot of applications otherwise also in real setups. For example, like, if you have a huge system, I mean, like a huge company, if you're running a company and with a lot of dynamics, okay, and then you want to see how to strategize something, right, devise some strategies and things. It's not possible to get a lot of data, and there'll be a lot of states, a lot of parameters and things like that. Okay, and if you model this appropriately as an NDP or with reinforcement learning kind of frameworks, you can use these approximate Q learning ideas like very well. It does really well in practice. Okay, so what I'll do is I'll stop here for now. Okay, and we'll again continue from tomorrow. Okay, so yeah, thanks everyone. I'll just hang back for some time if there are more questions. So if not, thanks a lot.